Hello students, today I am going to start the introduction part for the exercise 13.2, and the introduction part of this exercise involves with the two concepts. First one is the multiplication theorem on probability and the second one is independent events. So let's start. The first concept is multiplication theorem on probability. Multiplication theorem on probability. Theorem on probability. See here what this theorem says about the probability. Suppose E and F are any two events associated with the sample space S. Let E and F be any two events associated with the sample space S. Then probability of E intersection F, or you say that probability of E and F, and refers intersection here. So in probability, R refers union and refers intersection, and also R refers rule of addition, or and refers rule of multiplication. So probability of the events E and F is equals to probability of the event E into probability of the event F, given that the event E is already occurred, or 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 probability of the events E and F, probability of the events E and F is equals to probability of the event F into probability of the event E, given that F is already occurred. So this is what multiplication theorem on probability. So let us consider one example. To understand this. So a ball or an urn contains an urn contains two black balls and three red balls. And the experiment is two balls are drawn. Two balls are drawn. What is a or two balls are drawn successively without replacement without replacement. What is the probability that what is the what is the probability that first ball first ball being a black ball and second being a second being a red ball second being a red ball. See here the question is an urn in the sense box. A box consists two black balls and three red balls. And the experiment is two balls are drawn. Two balls are drawn successively in which manner? In without replacement manner. Replacement manners in the sense one ball is drawn and note down its colors, and then without replacing this first ball we need to take the second ball. So this is what without replacement manner. And the question is what is the probability that first ball being a black and second being a red ball. So required probability is here in this question. The required probability is required probability is probability of the first ball being red, sorry, first ball being black, probability of the first ball being black into probability of the second being red, probability of the red ball, given that the first ball is already occurred a black ball. I hope all of you understood. And this required probability is equals to, so probability of the first black ball. See here total number of balls in the blacks is 5. So divide by 5. And number of black balls is 2. Therefore 2 by 5 be the probability of the first black ball into probability of the red ball, probability of the red ball when first ball is black already occurred. It means one ball is already reduced in this box. It means total number of balls in the box is 4 because the manner is without replacement here. And total number of the balls in the box is 4, and in that the number of red balls is 3. Therefore 3 by 4 is the probability of second red ball. Hence the total required probability is equals to 2 ones are 2 twos are. So 3 divided by 5 twos are 10. So 3 by 10 is the probability of first ball being a black and second being a red ball. So let us consider one more example to understand this. So now the second question. So same question. Suppose an urn contains 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 two black balls and three red balls, and the experiment is two balls are drawn. Two balls are drawn. Here the manner is without replacement, but in the second question, two balls are drawn with replacement. With replacement. With replacement. And the question is, what is the probability that? What is the probability that? Probability that same condition. First ball being a black, first ball being a black, and and second being a red ball, and second being a red ball, second being a red ball. Now see here the difference between this first and second question is the way of drawing that two balls. In the first question he is taking or he is drawing the two balls in without replacement manner, but in this second question he is taking that two balls in which manner? In with replacement manner. So here also same thing, there is a box which consists two black balls, two black balls and three red balls, three red balls. With replacement means he has to choose one ball from the box and note down its colors and then keep back that ball to the box, and then he has to choose the second ball. This is what? With replacement manner. So therefore in this question the required probability is equals to required probability is equals to probability of the first ball being black into probability of the second is red, given that the first ball is already black ball is occurred. The probability of the first black ball is, so total number of balls in the box is 5, therefore divide by 5. Out of 5 there exist totally 2 black balls, therefore 2 by 5 is the probability of first black ball into, now he is choosing one more ball from this box, but in which manner? In a with replacement manner. It means that first he is to keep this drawn ball into the box. It means that still the total number of balls in the box is 5, so therefore divide by 5, and out of this 5 totally 3 red balls, therefore 3 by 5 will be the probability of that second ball being red. So totally required probability is equals to 2 into 3 6 divided by 5 into 5 25. So 6 by 25 is the probability of this first ball being a black and second ball being a red when two balls are drawn in with replacement. I hope all of you understood. Now observe here, in the first question, probability of the second ball depends upon the probability of first ball because the manner is without replacement manner. When a ball is drawn, it means that number of balls in the box reduces. But in the second question, this probability of second ball doesn't depends upon the first ball. It means if you draw one ball from the box and still he is returning to the box, it means total number of balls in the box remains same if you draw one or two or three balls from the box in a with replacement manner. It means that the second ball probability doesn't depends on the probability of the first ball. It means that these are nothing but independent events. These two are what? Independent events. So independent events in means independent events means, see here, what is the next concept of the introduction part of the exercise 13.2? Independent events. Independent events. Independent events means two events, two events, E and F, two events, E and F are said to be, are said to be independent events. Independent events. If same thing, probability of E intersection F is equals to probability of E into probability of F by E. But see here, if the manner is with replacement, probability of this second ball doesn't depends on the probability of first ball. It means that this probability of FB can be written as probability of F by E can be written as probability of F. So it means probability of E intersection F equals to probability of E into probability of F. If probability of E intersection F equals to probability of E into probability of F, then that two events are called independent events. Here in this question, no need to write probability of B into probability of R by B. We just write probability of R because the probability of this red ball doesn't depends on the probability of first black ball. Why? Because if you run one ball from the box in with replacement, it doesn't reduces the number of balls in the box. It means the second ball probability doesn't depends on first ball. It means that here these two events are independent events. So in independent events, we may replace this probability of R by B just by probability of R. So it means that two events E and F are said to be independent events if probability of E intersection F is equals to probability of E into probability of F. I hope all of you understood this concept. First one is a multiplication theorem on probability and the second one is independent events. So let's start solving some of the examples based on these two concepts. And here is the first question. And the first question is, here similar question with I considered in explanation. The question is, an urn contains 10 black balls and 5 white balls. Same thing, two balls are drawn from the urn one after the other without replacement. In which manner he is drawing that two balls? In without replacement manner. And the question is, what is the probability that the both drawn balls are black? So here we need to identify the probability of that both balls are drawn should be a black balls. So here an urn contains 10 black balls and 5 white balls. 5 white balls. So total number of balls, it means number of outcomes in the sample space is equals to 50. And required probability is equals to, required probability is equals to, see here, both drawn balls are black. Probability of the first black ball and probability of the second ball is also black, given that the first ball is already appeared a black ball. So the question is, he is taking that two balls in which manner? Without replacement manner. It means that the probability of second ball depends on the first ball. So it means probability of the first black ball. Total number of balls in the box is 15, and out of 15 totally 10 black balls. So 10 by 15 is the probability of first black ball into probability of second black ball. So he drawn one ball from the box in without replacement manner. It means the number of balls in the box reduces, and now the number of balls in the sample space is equals to 14 because one is already drawn. Therefore divide by 14, and out of this 14 totally there exist 9 black balls because one is already drawn. Therefore 9 by 14 be the probability of second black ball when the first ball black is already appeared. And now here you can cancel here. So 5 2s are 10, 5 3s are 15 into 9 divided by 14. And now 2 1s are 2 7s are 3 1s are 3 3s are. Hence 3 by 7 is the required probability that both the drawn balls are black. I hope all of you understood this question. Now let's start the next question. And the next question is, so see here. So this question related with the cards. So here 3 cards are drawn successively without replacement. So here also he is taking 2 cards from the pack in without replacement manner. And what is the probability that first 2 cards are kings and third card being an ace? So in this question he is drawing totally 3 cards out of 52 cards. So he is drawing or he is taking 3 cards, and what is the probability of first card being a king, second card being a king, and third card being an ace? And one more thing you need to observe here, these 3 cards are taking in which manner? In without replacement manner. So therefore required probability is equals to required probability is equals to, so probability of the king card into probability of the king card into probability of the ace card, or you can write it as probability of king card into probability of king card given that first is king appeared into probability of the ace card given that first 2 cards are kings. I hope all of you understood. And now see here, so required probability is equals to probability of the first king card. Total number of king cards in a pack is 4. Therefore 4 by 52 is the probability of first 2 king cards. And into probability of second king card, he is taking in without replacement manner. Therefore 3 divided by 51 is the probability of second king card into probability of the ace card. Total number of ace card in a pack is 4, divided by total number of cards is 52, but 2 cards are already drawn. Therefore 4 by 50 is the probability of ace, third ace card. And here you can simplify here. So first thing, 4 1s are 4 13s are into 3 1s are 3 17s are into 2 2s are 2 25s, which is equals to 2 divided by 13 into 17 into 25. 13 into 17 into 25. So multiply these three, you can get your answer. I hope all of you understood this question. Now let's start the next question. And the next question is, a die is thrown. See here, this is a question related to the die. A die is thrown. E is the event. Number appearing is a multiple of 3. See here, when a die is thrown, total number of possibilities are 6. Therefore, sample space is equals to 1, 2, 3, 4, 5, 6. And he has given that E is the event. Number appearing is a multiple of 3. It means event E is equals to multiples of 3 out of 6 is 3 and 6. Therefore, 3, 6 are the outcomes of the event E. And he also given one more event, F be the event. Number appearing is even. So in the event F, there exist only even numbers. Therefore, event F is equals to, even numbers are 2, 4, 6. 2, 4, 6. And his question is, then find whether E and F are independent. So we need to identify whether these two given events E and F are independent or not. So as you know that the definition of independent events, two events E and F are said to be independent events if probability of E intersection F is equals to probability of E into probability of F. So we need to check these three. So if probability of E intersection F equals to probability of E into probability of F, then we call these two given events are independent, otherwise not. So first we need to identify the probability of E. So directly here we can write probability of the event E is equals to 2 divided by 6, which is equals to 1 by 3. Similarly, probability of the event F is equals to 3 by 6, which is equals to 1 by 2. And we need E intersection F. E intersection F means common elements in E and F. There is only one common element in E and F, that is what? 6. Therefore, probability of, therefore, probability of E intersection F is equals to 1 divided by 6. Now observe here, probability of E intersection F is 1 by 6 and probability of E is 1 by 3 into probability of F is 1 by 2. So 1 by 2 into 1 by 3 is equals to 1 by 6, and which is equals to probability of E intersection F. It means that given two events E and F are independent events. Are what? Independent events. I hope all of you understood this question. Let's start the next question. And the next question is, see here, so this question is also related to the die. And the question is, an unbiased die, unbiased in the sense normal die, normal die. So probability of getting all numbers in equal chances. So biased in the sense there is no equal chances to get all the numbers. Such type of dies are considered as a biased die. So here he has given that unbiased die. Unbiased die means equal chance to get 1, 2, 3, 4, 5 and 6. So the question is, unbiased die is thrown twice, twice in the sense two times. When a die tossed twice, the number of outcomes in the sample space is equals to 36, as you already known from the 10th class only. And now the question is, let A be the event. Odd number appears on the first throw. See here. Here he has given that the event A, and event A is odd number appears on the first throw. It means first die must shows either 1 or 3 or 5. Therefore, the outcomes of the event A is 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, and then 3 1, 3 2, 3 3, 3 4, 3 5, 3 6, and then 5 1, 5 2, 5 3, 5 4, 5 5 and 5 6. So these are the only outcomes of the event A in which the first die is showing odd number. And then second event is B. B event is odd number appears on the second throw. So in this event B, second die must show either 1, 3 or 5. Therefore the outcomes of the event B is, outcomes of the event B is 1 1, 1 3, 1 5, and then 2 1, 2 3, 2 5. Here observe second die showing odd numbers are 3 1, 3 3, 3 5, and then 4 1, 4 3, 4 5, or 5 1, 5 3, 5 5, or 6 1, 6 3, 6 5. So these are the only possible outcomes of the event B. And the question is, check the independence of the events A and B. So here we need to identify whether these two events A and B are independent or not. Now observe this event A. In event A, in this event A, number of outcomes is equals to 18. Similarly, in this event B, number of outcomes is also equals to 8. Number of events or outcomes in the event A is 18, and number of outcomes in the event B is also 18. Therefore, probability of event A is equals to 18 divided by 36, which is equals to 1 by 2. Similarly, probability of the event B is also 18 by 36, which is equals to 1 by 2. Now, to check the independence of these two events, we need to identify A intersection B. Now what? A intersection B. Now observe here, in event A, only first die showing odd number. In event B, second die showing odd numbers. It means the common outcomes in event A and B means first and second, both the die shows odd number. In which outcome, both die showing odd numbers are belongs to intersection B, that is A intersection B. So here the common outcomes is 1, 1, 1, 1. First one is 1, 1. And then observe here 1, 3. So 1, 3. 1, 3. And then 1, 5. Here 1, 5. And then 3, 1. So here 3, 1. And then 3, 3. And then 3, 5. And then 5, 1. And then 5, 3. And then 5, 5. These are the only outcomes. So next outcome is what? 3, 1. And then 3, 3. And then 3, 5. And then 5, 1. And then 5, 3. And then 5, 5. These are the only outcomes of the events A intersection B. Therefore, probability of A intersection B is equals to probability of A intersection B is equals to. So, number of outcomes in A intersection B 1, 2, 3, 4, 5, 6, 7, 8, 9. So, probability of A intersection B is 9 divided by 36, which is equals to 9 ones are 9 fours. Therefore, probability of A intersection B is 1 by 4. Now, what to identify the independence? Consider probability of A into probability of B, which is equals to probability of A is 1 by 2 into probability of B is also 1 by 2, which is equals to 1 by 4, and this is equals to what? Probability of A intersection B. So since probability of A intersection B equals to probability of A into probability of B, which implies given two events A and B are independent events. I hope all of you understood this question. Let's start the next question. And the next question is, so here the question is, three coins are tossed simultaneously. In this question, three coins are tossed simultaneously. When three coins are tossed, the sample space is H, 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 T, H, T, H, T, H, H, or T, 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 H, T, H, T, or H, T, T. So these are the outcomes of the sample space when three coins are tossed. So total number of outcomes is 8. And the question is, consider the events. Event E is 3 heads or 3 tails. Here in this question, event E is given. Event E is what? 3 heads or 3 tails. So these are the only two possible outcomes of the event E. And then F is at least 2 heads. At least in the sense greater than or equal to 2 heads. It means either 2 heads or 3 heads. So therefore, outcomes of the event F is 2 heads means H, H, T, or H, T, H, or T, H, H, or 3 heads. 3 heads means H, H, H. And now he has given that the event G also. Event G is at most 2 heads. At most in the sense less than or equal to 2 heads. Less than or equal to 2 heads means either 0 heads or 1 heads or 2 heads. So therefore, outcomes of the event G is firstly outcomes with 0 number of heads. That is what? Tail, tail, tail. And outcomes with 1 head. That is HTT or THT or TTH. So these are the only 3 outcomes with 1 heads. And then number of outcomes with 2 heads. 2 heads is HHT or HTH or THH. So these are the only 3 outcomes with 2 number of heads. So we write all E, F and G events, and the question is, see here, of the pairs EF, EZ and FZ, which are independent and which are dependent. So we need to identify whether E and F are independent or not, and E and G are independent or not, and F and G are independent or not. So first we need to identify probabilities of all these three events. See here. Probability of the event E. Directly we can write 2 divided by 8, which is equals to 1 by 4. And probability of the event F is equals to 4 divided by 8, which is equals to 1 by 2. And probability of the event G is equals to 7 by 8, because totally 7 outcomes in G. And now to identify the E and F are independent or not, we need to check whether probability of E intersection F is equals to probability of E into probability of F or not. So for that we need what? We need E intersection F, and for E and G we need E intersection G, and for F and G we need F intersection G. Therefore firstly I am going to write all these. So first one what? E intersection F. So common outcomes in E and F. See here, there is only one common outcome, that is H, H, H. So therefore H, H, H. So which implies probability of E intersection F, which implies probability of E intersection F is equals to 1 by 8. Now we need E intersection G for the second pair. Now what? E intersection G. Common outcomes in E and G. The common outcome is only one, that is what? T, T, T. T, T, T is common in E and G. Therefore, E intersection G is T, 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 which implies probability of E intersection G is also equal to 1 by 8. And now for the third pair, we need F intersection G. Now what we need? F intersection G. So common outcomes in F and G. So there is only common outcomes in F and G is HHT, and then HTH, HTH, and then THH, THS. So these are the only three outcomes common in F and G. H, HT, HTH, HTH, and then THH. So these are the three outcomes common in F and G. Therefore, probability of F intersection G is equals to 3 by 8. Now for identifying whether E and F are independent or not, consider what? Probability of E into probability of F, which is equals to probability of E is 1 by 4 into probability of F is 1 by 2, which is equals to 1 by 8, and which is equals to probability of E intersection F. And this is equals to what? Probability of E intersection F, which is equals to probability of E intersection F. It means the pair EF or E and F events are what? Independent or independent. I hope all of you understanding. Now for the second pair, consider. Now what? Consider probability of E into probability of G. Probability of E into probability of G, where probability of E is 1 by 4 into probability of G is 7 by 8, which is equals to 7 divided by 4 8 is a 32, and 7 by 32 is not equal to probability of E intersection G, which is not equal to probability of E intersection G. It means the pair or the events E and G are not independent, it means they are dependent events. I hope all of you understood. Now for the third pair, F and G, consider probability of F into probability of G into probability of G, where probability of F is 1 by 2, 1 by 2 into probability of G is 7 by 8, 7 by 8, which is equals to 7 by 16, and 7 by 16 is not equal to 3 by 8. It is nothing but it is not equal to probability of F intersection G. It means the pair FG are the events F and G are not independent. It means they are dependent events. Dependent events. I hope all of you understood this question.